Do you know buildings behave like a vertical cantilever when wind loads are applied? In this lecture, I will talk about lateral stability and stability systems in steel framed buildings. This is part 23rd of lecture series on steel design. For other parts, please have a look at link down below. Hey friends, if you're new here, I am Dr. Javed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life. So the purpose of today's lecture is to talk about lateral stability of steel buildings, which is very important. Up to now, we have covered design of structural elements, which means that we have covered detailed design of tension members, detailed design of compression members, detailed design of restrained and unrestrained beams, and detailed design of plate girders. But we have talked about the components. But the main thing I will talk about today is the lateral stability. How a building is going to resist lateral load, and what kind of mechanisms are you going to provide to resist lateral loading? Are you going to use shear walls? Are you going to use bracing? Then how do we design them? And crucially, I would like to cover the overall structural behavior, the global behavior. What happens when we have a frame, how it's going to resist the horizontal load. Today's presentation will give you detailed design of lateral stability systems. Lateral stability systems can include shear walls, it can include bracing. I have divided lateral stability in steel buildings into four parts. First part, which I'm going to talk about today, is part 23 of 30-part lecture series on steel design. This is lateral stability and stability systems. The second part is part 24, which is about braced framing and moment frames. The third part is part 25, which is a tutorial on wind loading calculation. The final part, part 26, is about stability analysis, where I'll be working out alpha critical. This is how my presentation is organized today. So first introduction, then lateral stability, then stability systems, then braced framing, then moment frames, and then shear walls, and then examples, and then resources. What I will not cover in detail is the moment frames. So lateral stability can be provided in a number of ways. It can be provided by using shear walls. It can be provided by using bracing, and it can be provided by having rigid connections. Most of the time in buildings, we have pinned connections, which means that they cannot take moment. When they cannot take moment, it means that they can rotate at the ends. So if I do not provide any bracing, your structure is not going to be stable. It will be unstable. That is the reason we provide bracing, to make it stable and also to take horizontal loads. But there could be other way where we use moment frames. If we have large portal frames, if we have large warehouses, in those we use moment frames. It means that we use rigid joints which can take moment, which can transfer moment from members to the joint. As such, we do not need bracing or shear walls. My examples will not cover moment frames, but I will briefly cover what they are, where do we use them, so that you know that these are there. What is stability? European Council Construction Product Directive defines building to be stable when the loadings are liable to act on it during its construction and use. The structure is not going to collapse. So stable structure will not collapse. Stable structure will not have major deformations. They will not deflect much. Firstly, for stable structure, we have to avoid collapse of the structure or part of the structure. Secondly, it will not have much deformations. Third is related to mainly serviceability, so that the deflections are not much to cause the damage to any part. And fourthly, the damage should not cause disproportionate collapse to original cause. So that is related to robustness of structure. By robustness of a structure, I mean that in the event of any local failure, it should not propagate to the entire building, as such causes the disproportionate collapse to the original cause. The research in robustness and disproportionate collapse, it started back in 1969 when there was a tower block termed as Ronan Point, not very far from Canning Town Tube Station. It was 24-story tower block. A gas explosion happened on part of 22nd story, and then the entire part of the block collapsed down. And the key reason for
its collapse was the building was constructed through blocks. Blocks were stacked on top of each other, so they were not connected with each other. And then after that, this research on robustness and disproportionate collapse started around the world, which means that any frame in a structure has to be connected with other parts of the structure. So if one part fails, the load is distributed to other parts of the structure without causing catastrophic failure. Stability comes with two parts, safety and function. Safety is related with ULS, ultimate limit state, where we check the strength of the structure. And then we have function, where we talk about the use of the structure, and that is related to serviceability. So serviceability is most of the time related with deflections, vibrations, which will affect the finishes and other stuff. But safety is of prime importance. Stability can be a local or global behavior. For example, here you can see that this is local buckling of the column. Column or flange buckling is local buckling. It is local to the column. And the overall column buckling, flexural buckling, is termed as global buckling, but it is local to the structure. If I have a 10-story structure, if this only one column is buckling, it will be local to the structure. But normally, when we talk about element basis, then when we have small portion being affected by buckling, we say that it's local buckling. When the entire member is undergoing some kind of instability, then we say that it is the global buckling. Now, building subjected to wind load is termed as global. So it will cause global buckling. It means that if I have a 20-story building, if wind is blowing, it will cause global buckling of the entire structure. Now, up to now, we have covered how do we take into account local buckling, that is through section classification, and how do we take into account global buckling, that can be flexural buckling in columns, and that can be lateral torsional buckling in beams. So we have covered these. But what we have not covered is the buckling that is truly global in nature, that is the entire building, that is the entire structure. So when wind blows, it affects the entire building. So if there is no stability system, then entire building is going to be affected. Now, forms of instability. Instability can happen in a number of forms. So firstly, we have overturning. So that is denoted here, when a building can overturn because of this horizontal load. And then we have this sliding, when the structure can slide when we apply loading. And third, we have racking. Here you can see that the building has moved to the right side. Finally, we have twisting. So when a building can twist. So these are forms of instability for buildings. Now, lateral stability. What does it mean by lateral stability? Why a structure needs lateral stability system? Lateral means sideways or horizontal versus vertical gravity load. So gravity load is considered to be vertical and horizontal load is considered to be lateral. Now, what causes lateral loads? Wind and seismic action, they cause lateral loads. But in the UK, we don't have much seismic activity, so we almost don't design or teach the seismic effects. But the principle is literally the same. Now, the key thing to remember here is that when these loads are acting on the beam, you can see how this building is being twisted, how the building is deflecting. Then a building can be thought of a vertical cantilever. So a cantilever is fixed at the bottom and it is free at the top. So it behaves like a vertical cantilever. Under the action of wind loading, a building, if I simplify it, it behaves like a cantilever. Now, horizontal loads due to imperfections, they should be accounted for. Now, these are termed as equivalent horizontal loads or EHF. Normally, we take 1 over 200 of vertical loads as EHF or 0.5% of vertical gravity loads. Now, in old design codes, we used to call them as notional horizontal loads. What is the cause of these loads? These loads come from misalignment. It comes from out of straightness of members. It comes from building errors. So the way Eurocode takes into account these loads is by equivalent horizontal forces, which we term as EHF. And then wind loading. Wind loading is certainly a very difficult and complex phenomena. For normal buildings, we use BS 1991 1 part 4. So we use Eurocode 1. And what guidelines do we use? We can use these tools. So if you click on these tools, you will be able to see this wind loading calculator by using these different parameters. If you have very tall buildings, then normally you use wind tunnel test. The procedure that I'm going to talk about is for ordinary simple buildings. But if you have very tall buildings, then you have to carry out wind tunnel test to see that how wind pressures are coming. Now, how do we work out the peak velocity pressure? Peak velocity pressure for different areas in the UK in kilonewton per meter square, that is wind pressure, is given. So you can see that for City of London high rise, the maximum is 1.09, the minimum is 0.55. So we normally use the mean. So most of the time, if you discard this Dover cliff top, most of the time we get these values which are 1 or less than 1. So as a rule of thumb, if you're not working out wind pressure through detailed procedure, which I'm going to talk about in a minute, then you can roughly use this 1 kilonewton per meter square as estimated wind pressure just for your concepts and scheme designs. But at some point you have to work out the detailed wind force, which I'm going to talk about in a bit. So wind loading, how do we work out wind loading? Now, if I estimate it as 1 kilonewton per meter square as wind pressure, this is a rule of thumb, remember. That's not the exact wind velocity pressure that's going to come out as a result of a detailed procedure, which I'll talk about in a minute. So consider if you have this building 20 meter wide, 27 meter high. So B, D, and H, so length, width, and height of the building are given. If the wind pressure is 1 kilonewton per meter square, so wind blowing on red face will be, so you'll multiply height with the width of the building and then with this pressure, 1 kilonewton per meter square. In that way, you will get the total load. If you want to work out load on the longer face, which is 29 meter, then you will multiply the longer dimensions. So 29 times 27 is height times 1. 1 is the wind pressure. So in that way, you will get 783 kilonewton. Now this is a simple example, but the detailed example will come later where we will exactly work out wind pressure. Now remember, once again, that wind which is blowing on the short face, which is 20 millimeter, lateral stability system that you provide on the longer face will resist that. And wind that is blowing on the longer face, the lateral stability system that you provide here, for example, if you provide bracing here, this wind force will be resisted by that bracing. So this is very important thing to remember, that when wind pressure is being applied on the face, wherever you have frame, the frame is going to try to move in this direction. So the entire frame will move in this direction. So the only thing that will stop it from moving will be shear wall or bracing provided on the long face. So just to sum this concept up, wind blowing on short face will go on the lateral stability system provided on long face. In the same way, wind blowing on the long face will come on the lateral stability system that you provide on short face. This is very important to understand. Now, another very important thing here is wind load at each level is calculated from level height and exposed width of the building for direction of wind blowing. So for example, if I want to work out total load at roof, this is roof level, and the effective height, I will consider only the height which is at the bottom. There is nothing at the top. So this is roof level. So if building is 20 meter wide, wind load is 1 kilonewton per meter, each floor is 3 meter high, each floor will get 20 into 3 into 1. The key thing here is that at a floor level, you can see that this is the wind force. Wind is entering from this side and it is exiting from on the leeward side. This is windward side. The height that we are going to consider for this wind loading is going to be half of the height at the top and half of the height at the bottom. So it means that this wind force is going to cover these two heights, half height above and half height below. So if height of each floor is say 3 meter, then obviously it's going to be fine. You just take 3 meters. If this is 3 meters and if the bottom one is 5 meter, then simply you take average. So half of 3 is 1.5, half of 5 is 2.5. So you simply add them up. So that's how we work out wind loading. Now P delta effects. These P delta effects are very important. And the way we incorporate this effect is using alpha critical in Eurocode. Now buildings move in horizontal direction and this causes horizontal deflection. The vertical load or P that caused this moment due to horizontal deflection That is termed as P delta effect. If I have this member, if vertical load is applied, and this is the deflected shape, if this is deflecting too much, then this vertical load is going to cause moment as well. So that moment is termed as P delta effect. So this will not only generate a vertical load, but because of the geometry, it is going to cause some kind of P delta effect. So for P delta effect, we have to evaluate the second order analysis, all right, which means that we have to carry out nonlinear buckling analysis, which will always give us the accurate results. Normally, for analyzing buildings, we use first order analysis, which means the linear analysis. Eurocode 3 provides a very simple method to quantify severity of this P delta effect. Now here you can see P delta effects. Now this is initial state, and then again you have first order analysis. So when the force is under action of horizontal vertical load, if it is not causing a lot of deflection due to applied load, then we carry out linear analysis. If the vertical force is high and horizontal force is really high, then it will cause very high deflection, and this vertical load is going to cause some kind of moment. That moment has to be resisted by reaction over here. This is what we call as second order effects or P delta effects. Now Eurocode has a procedure where we call this HED, means horizontal load due to P delta, which is here. HED is equal to stiffness of the spring into delta H P delta, into deflection into P delta. We have this formula HED is equal to P delta, which is equal to HED plus VED. Again, if we rearrange this formula, we will come up with this formula where HED P delta is equal to this. HED P delta is the resultant horizontal force transmitted by each story, and HED is the total horizontal force including EHF. This is resultant force by each story. And VED is the total vertical design force acting on a story. H is the story height, and delta HPH is the inter-story second order horizontal displacement. We say that VCR is equal to KH, this value, and alpha critical is equal to VCR over VD, where the formula comes out to be this. So alpha critical can be found out using first order analysis, which is the formula for alpha critical is this one. There is a limit. If alpha critical is less than 10 or something, then we don't need to consider second order effects. I will come to this later in a minute in the example. Now, before I do that, I would like to talk about stability systems. How the loading is transferred from the wind load all the way to foundations. Now, in here, wind load is applied here. Firstly, it touches the roof. It touches the horizontal bracing. And through horizontal bracing, it is transferred to these members. Again, goes to horizontal bracing. It is transferred to these members. Now, you would say that why there are not any arrows in this middle section. So I would say that consider it as a truss. So if you have a truss element, if you have 2 and 2 panels on the side, the middle element will not take any load. So that's why there are no arrows there. So it's not taking any forces. The force travels all the way through here, through roof bracing to the bracing over here. It goes at the top and then again gets transferred here, and then from here through bracing to the columns, and again down through the floor to the column, and then finally it goes to the foundation. Wind gets transferred the way the loading path is, so from wind load to facade. So it firstly goes to facade, and then it goes to horizontal bracing, and then it goes to vertical bracing, and then it goes to the foundations. So it is very important to understand the wind path. So let me move on to horizontal bracing. Now normally slabs do the job. If you have a concrete slab or if you have a composite slab, normally they act as horizontal bracing. But if you have a very thin sheeting without any concrete, without any slab on top of that, for very thin sheetings, they don't do the job. So for them, we use horizontal bracings. The horizontal bracing is provided in the slab where you have very thin sheeting. Concrete or composite slabs, they act as diaphragm, which means that they transfer the forces. So attention with precast units, topping is usually sufficient. Some kind of horizontal bracings where we're providing horizontal bracing in these members, and here we have a void. Again, some other examples of limited stiffness because of these voids. We have bracing here. In this example, you can see that how the load is transferred. Now, what happens if there is no slab at top of the structure? That can happen when we have portal frames. We use portal frames when we have very large spans in warehouses and in large supermarkets. So in that case, we provide the horizontal arrangement. The roof bracing that you see here, and that is represented in this figure here, this is provided to resist lateral loads. And then vertical bracings, we use vertical bracing across the entire building. We distribute it across the entire building. We used to provide it for stability. And you can see that this is the bracing arrangement. We used to provide it in such a way so that it does not disturb the services. And also we use to provide it some kind of extra redundancy so that your structure is redundant. You have various examples of these bracings. So simply I would say that you just have a look at it. I will not cover it in detail. This has been taken from this reference, Stability of Buildings, Part 1 and 2 by I. Then how do we work out overturning moment and how do we work out forces in vertical bracing? The moment is equal to force into distance. Remember that building acts as a vertical cantilever when we are using horizontal loading. We are starting from here. The height of this floor is h. H is a force times h. It gives us this force. And then h times 2h will give us second force. Similarly, h times 3h will give us third force and fourth and fifth force. So in total, we have 15 h, capital H times h. This is giving us the total moment. So forces in vertical bracing, moment is equal to force into distance, and force is equal to moment over distance. Moment is 15 h times h, and the distance is d, which you can see over here. There will be equal forces. Now these are forces in vertical bracing, and forces will be equal in tension and compression. Now how much horizontal forces we have? The total horizontal forces are 5h, which is summation of these forces. In vertical bracing, we have braced systems where all joints are assumed to be pinned, which means that the joints cannot take any moment from members to the joints. Typically, we use these braced systems for buildings. And the definition of this brace system is that all frame joints are pinned, which means that no moment is transferred to the joints, and the stability is provided by bracing or shear walls. Now here you can see that this is example of braced frames, where you can see that stability to the building is provided by either bracing or shear wall. Now key thing here is joints are pinned. You can combine bracing with shear walls and then say that okay, this is a braced system. So two things, in a braced system or in a braced frame, joints are pinned and stability is provided by bracing or shear walls. So this is a simple definition of a braced frame. Unbraced frame means that frame itself is stable, it does not require any stability. And stability in these frames is provided by rigid connections or rigid joints. And by rigid joints, I mean that joints are rigidly connected to each other and moment is transferred from members to the joints. Now, in buildings, we rarely see total moment connections. Most of the time, we see these braced frames. And then there is hybrid system. Hybrid system means that on one side of the frame, we use brace system. On other side of the frame, we use moment joints. Orthogonal in single direction. So here you can see that we have moment connection. We have wall or bracing. This is single axis hybrid, and this is orthogonal axis hybrid. It means that we have bracing on one part of the frame. Now these dots that you can see here, they represent moment connection. So on the one side, we resist wind loading through bracing. On the other side, we resist loading through moment connections, which are here. This is how we show moment frame. And again, this is how we show a braced frame. And this is how we show a wall with penetrations, some kind of doors and windows. So usually at some point, because of architectural reasons, because of doors and windows, sometimes bracing is very difficult difficult to provide. But these are the most common stability systems in buildings. Vertical bracing, how do we provide vertical bracing? This is the plan of the building, and at the bottom you can see these sections. You can see that at both sides of the frames, the bracing is provided here at specific locations. Two-way braced. It means that on both sides of the frame, we use bracing. Now, this is orthogonal braced. It means that on one side, section is being taken over here. It means that if we cut this building across the depth, we will see these kind of structures. The wind loading along the long face is resisted by moment connections, and wind loading along the short face is resisted by this bracing. Again, here it is two-way moment frame. It means that in both directions, X and Y, the wind loading is resisted by moment connections.